What's up, my friend? Let's try to get this. No hat! Hat out, guitar in. I heard you were doing a live concert. Had to tune back in. There is a handout. I just put it up a couple minutes ago. How are you guys doing today? Did I not put it up there? Oh, wait. Oh, you're right. Okay. Might be. Okay, I'm putting the handout up right now. Man, I thought I put it up. My bad. Okay. There we go. Post that. Okay, now it should be up on UB Learns. The handout is up. Are you improvising? These are little ditties I'm familiar with that I've come up with. Taking song requests. I don't know that many songs though. I guess we could look up the chords. We could do that. Some Dragon Force? That's right. highway in the sun. Yeah, I love that song. I love the band America. Well, they only have, in my opinion, a couple really, really great songs. Like Ventura Highway, of course. Horse with No Name. Sister Golden Hair, right? But other than that, what does America have? The band. Oh yeah, Brad plays drums like a monster. You would buy that album? We got to think about it. We got to get to work on that. How's Labor Day treating you guys? Laborious. A laborious Labor Day. Yeah, I mean it is. The homework is laborful. It is a little dense. I'll give you that. There's a lot of review stuff in there. It's like dusting off the cobwebs, refreshing that dynamic systems stuff. Been learning some Led Zeppelin today. Good for you. So you guys, I did post an announcement earlier. So the homework 1 did get extended till Wednesday, 2 p.m. So if you're still laboring on that, I'm going to be there for office hours this afternoon. Question 2D basically covered the whole 340 course. That is a good summary. That is a good summary. So I'm going to be on Discord at 4:30 to 5:30. So come hash some stuff out. But I hope you guys are having a good Labor Day. You have a Discord for flight dynamics? Can I have access even though I have Dr. Lagore? I don't mind. Shoot me an email. I'll send you the link, or have a friend send you the link if you have a friend in this section. I hope you have a good one too. Hey, thanks, Miracle. All right, guys. I know I got the handout out a little late today. I try to get them out earlier than 1 minute in advance, so I apologize for that. I do. Today, we're looking at reference frames, coordinate transformations. So this is all working towards deriving the aircraft equations of motion. So we've talked a little bit about, in this class, it's going to be common for us to have nonlinear equations of motion. And our response to that is typically to linearize in this course. So we're working towards those equations of motion for the aircraft, and the place to start is kinematics. So if you're following along, kinematics are translational and rotational positions, velocities, and accelerations. So kinematics is all of the motion in absence of forces. So it's position, velocity, acceleration, translational, and rotational. So we're doing kinematics for the next like 2 weeks, I think, for aircraft. And so today we're getting that kicked off, and we're going to begin with the pose of an aircraft. So what is the pose? The pose of an aircraft is the specification of its position, number one, and its orientation. And when we talk about orientation of an aircraft or a spacecraft, this is also commonly referred to as the attitude of the aircraft. So that's its orientation in space, like where it's pointing. Okay, so if we want to specify the pose, we can do that by defining a position vector of the aircraft CG, center of gravity, relative to a fixed frame. And additionally, to get the attitude or orientation, we have to define the relationship between the fixed frame and the body frame of the aircraft using a rotation matrix. So I have a little diagram down here. Okay. So we have a fixed frame down here in blue. And then we have the body frame attached to the aircraft. So let's first define a reference frame really quick. It's a perspective from which to make an observation. So the sensors on an aircraft, they're going to be mounted rigidly to the aircraft, and so they're giving us readings in this body frame in purple. And then we're going to have to relate that stuff back to an inertial frame or like a fixed frame. So that's where coordinate transformations are going to practically come in. So we're going to come back to this drawing, but I just want to give some notation for each of these frames. And I think this is the same notation that you would have in intermediate dynamics with Dr. Darrell. But when you define a frame, there's a couple pieces. So number one, you have the origin of the frame. So like for the fixed frame, we have point O, it's fixed there. And then you describe the 1, 2, and 3 basis vectors. So just to make that real clear, the origin of the frame is this first one. And then this is called a triad of unit basis vectors. And unit just means length 1. So let's define the body frame as well. So the body frame for an aircraft is located, well, the origin is at the CG of the aircraft, and I'm calling that point G. And if you go back up to the figure, you see G is sitting right there on the CG. And then our 3 unit basis vectors, we're going to call them BX, BY, and BZ. And the body frame for an aircraft, there's a pretty standard way of defining it. And it's interesting, it's the same thing. Does G have to be a vector? G is not a vector. G is just a point. So G is just specifying the origin of that. Okay. I guess you could define the position of the origin relative to another reference frame and then specify the coordinates of that point with a vector. But yeah, it's just the origin of the frame. So for the body frame for an aircraft, the x coordinate goes right from the CG out the nose of the aircraft. And then the y vector goes right down the right wing. So if you're the pilot, your right hand is pointing in the direction of y, and then the z vector goes straight down, which seems kind of opposite of what you might think. You know, z, we're flying, shouldn't it be pointed up? No, it's pointed straight down on an aircraft. Same thing with cars. The SAE coordinate system for a car has the z vector going down into the pavement, but the x and y is the same. X points out your windshield, y is pointing to the passenger side of the vehicle. If you drive in the United States, that is. I guess it would be the left if you're UK, but. Okay, so let's specify a position vector. So I kind of already sketched it in here. But we're going to go from this fixed frame origin to the CG of the aircraft. And this vector, we're going to specify it like this. I'm going to call it R with the arrow on top. I'm retraining myself to draw vectors in this way. So this is the position of G. I'm going to try to stick consistent with these colors relative to O. So that's the position vector G relative to O, the position vector of the aircraft. So what we're going to do is we're going to express this vector first in fixed frame coordinates. So in frame F. So we're going to do that down here. So position vector components. The position of the CG of the aircraft relative to the fixed frame is this R vector of G relative to O. And when I put these brackets and then put the F, that's just showing that I'm going to put this with fixed frame components, which you'll see here. So there's going to be an FX component, an FY component, and an FZ component. And I'm just going to call these X, Y, and Z for now. Kind of generic. All right. So this way of writing a vector, we call it basis vector notation. It's where you explicitly write out the basis vectors you're using, so Fx, Fy, Fz, and then these X, Y, and Z, these are what we call the coordinates. So another way of writing this vector, an equivalent way, which I'm sure you're familiar with, we can organize it in a vector. And this F down here, once again, is just telling us that these are components with respect to the F coordinate system. Which notation do you prefer and why? When I'm writing stuff out by hand, I don't know, I kind of like the basis vector notation, but this array notation is especially useful once we're actually doing computations. So taking things into MATLAB, when we have, so by the end of this lecture, we're going to derive a rotation matrix. And so anytime you're doing coordinate transformations, using array notation is the way to go. So I guess normally I prefer array notation. Okay. So let's talk about the coordinates of a vector. So I just defined them as x, y, z here. You can recover the coordinates of a vector with respect to a frame by projecting the vector onto the basis vectors of that frame. And the way we do these projections is using the dot product operation. So that's how you get components along basis vectors. It's basically casting a shadow from the vector onto that basis vector to see that component. So we'll do a quick example to show what this projection looks like for this position vector that we just defined. Okay, so this example is just verifying the components of this vector with respect to the f-frame. So to project a vector onto a basis vector, you take the dot product. So I'm taking the dot product of the position vector with respect to the basis vector fx, and this will give me the projected component along fx. Okay, so let's just substitute in here this vector. So these are the components once again. Trying to stick with these cool colors. Okay, so let's the dot product distributes. So I'm going to have fx dotted to fx, fy dotted into fx, and then finally fz dotted into fx. Now, if vectors are orthogonal to each other and you take the dot product, meaning they're 90 degrees from one another, the dot product goes to 0. A little on in the notes I show the definition of the dot product with respect to the angle between the vectors. And basically you have a cosine of the angle between the vectors that shows up, if you remember the dot product definition. So if you have cosine of 90 degrees, it goes to 0. So these are orthogonal to each other, that goes to 0. This is going to go to 1 because there's 0 degrees between them. They're the same vector. And the magnitude of, so they're just unit vectors. So that's why this goes to 1. So the component of this vector along f of x is x. So, I mean, this is what we defined it to be, so I'm just showing that this projection operation returns the component that you would expect to see there. So if you did the same thing, if you dotted that vector with fy, that basis vector, well, it would give you back that component along the y basis vector that we expect. Same thing with this, z. So if you want to bring this all together, the position of our aircraft with respect to the fixed frame, with the components expressed in the fixed frame as well, well, these are going to be the components that we just derived above. So we show that that comes out to x, y, and z. And like I said, I want to show you some dot product properties. Let's start with some notation. So I've been showing you just a dot for the dot product, but another way you might see this, you've probably seen this, if you have the transpose of a vector operating on V. So this is also called the dot product. You could also see it this way. Sometimes when it's written this way, it's called the inner product. So these are three ways you might see it. Now, the dot product, it doesn't matter the order, like I have U dotted into V, but you could also write it as v dot into u. You get the same result. So v transpose u, or in that other notation. So that's just a good thing to tuck away in the back of your mind. Whenever you're dotting two vectors together, it doesn't matter the order. And I mentioned that the dot product involves the angle between two vectors. So let's take u and v. So the definition of the dot product is, it's a scalar result, right? It just returns a number. It doesn't return another vector. And the number is the magnitude of the vector u multiplied with the magnitude of the vector v, and then the cosine of the angle between them. So that's why the dot product of orthogonal vectors goes to 0, because the angle is 90 degrees, cosine of 90 is 0. And if we're taking the dot product of unit vectors, well, their magnitudes will be 1. So 1 times 1, so evaluates to 1 for unit vectors. That's mostly why we work with unit vectors for coordinate systems. It's just easier. Okay, that's a little dot product notation. Let's talk about coordinate transformations, okay? So we took the position of the aircraft. So we say the center of gravity relative to the fixed frame origin. We wrote it in F coordinates, but what if we want to express it in the body frame coordinates? So I put a sub B here. So I want to express this vector with respect to the triad bx, by, bz. How do we do that? Well, using the procedure above, we know we can project the vector, and let's say, like, I know the vector components with respect to f. They're x, y, z. Let's just say I know this. Well, I can project that vector onto the basis vectors bx, by, bz using this dot product. So this would be the projection onto bx, and this would be, you know, the bx component, by component, etc., etc. But you guys have taken intermediate dynamics, and you know that in practice, the most straightforward way to transform between coordinate systems, we probably won't do this kind of dot product operation. We're going to use a rotation matrix to transform from one set of coordinates to another. So I'm going to go through a basic way of building this rotation matrix, specifically the direction cosine matrix. And on Wednesday, we'll go more into Euler angles, and beyond that, we'll even talk about quaternions a little bit. But we're not there yet. So I want to express that position vector relative to the body frame coordinates. So we're going to use a rotation matrix, and the one way of building this is to start by expressing the basis vectors of the B frame in terms of the F frame. And we will use projection to build up to this point. So let's go through this. So I want to express the basis vector Bx in terms of Fx, Fy, and Fz, right? So I'm going to project Bx onto Fx, and that'll be the coordinate along Fx. And I'm going to do that with these other ones as well. So I'm going to project Bx onto Fy and onto Fz. All right, let's use the definition of the dot product. Let's be consistent with the colors here. I'm filling this in kind of all over the place because I want to stick with these colors. But I'm just substituting in the definition of the dot product we used up above. So this first one, bx, fx, so I take the magnitude of them, and then I take the cosine of the angle between them. So I'll call alpha 1, 1, the angle between bx and fx. Alpha 1, 2, alpha 1, 3. So 1, 2 is the angle between bx and fy. 1, 3 is the angle between bx and fz. And we know because we defined all of these basis vectors to be unit vectors, these magnitudes are going to evaluate to 1. And we're just left with cosine alpha 1, 1, cosine alpha 1, 2, cosine alpha 1, 3. And then I just made a little reminder note here. Alpha 1, 1 is the angle between bx and fx. So this is bx expressed in the f-frame components. It just boils down to the cosine of the angle between each of these vectors. So if you did the same thing for the other basis vectors like by and bz, let's just fill those in, knowing that we're just going to end up with the cosine of the angles between these as the components here. Now this next part is where the rotation matrix comes in. Because I can take these three vector equations, bx, by, and bz, and you can organize this in what we call vectrix notation. So it's kind of a bridge between vector and matrix. So on this side, I'm going to have bx, by, bz, and I know how these are related to fx, fy, and fz. So like from our bx equation, I know it's cosine of alpha 1, 1 times fx plus cosine alpha 1, 2 times fy, cosine alpha 1, 3 times fz. And now you can see why I named these like 2, 1, 2, 2, and so on, because they correspond to the locations within this matrix. And I think you can also see why they call this a direction cosine matrix, because each entry is a cosine of the angle between two basis vectors. So once you fill in that matrix, we're going to call this, we're going to use R. I think Dr. Darrell used kind of like a capital T with a scripty thing. We're going to use R for rotation matrix. And we're going to have these superscripts. So this is going to be the rotation matrix that relates the frame F to the frame B. So here I say that on the right. The rotation matrix from F to B. Is this coming back to you guys, or you're like, I remember this from intermediate dynamics? So rotation matrix, you can also call it transformation matrix, and like I said, a direction cosine matrix, but they all mean the same thing. All right, so how do you apply this? Well, once you have this matrix, we can use it to transform vectors between F and B coordinate systems as follows. So let's say I want to get this position vector in terms of the basis v. And what I have is the vector with respect to f. Look at this commitment to the color. That takes a little effort right there. But I'm getting pretty agile about just swapping the colors in and out. Okay, so say I have that vector. I'm going to operate on that using the rotation matrix from F to B. The consistency. Right, so here we're taking the position vector in the F frame coordinates and transforming it into the B coordinates using that rotation matrix. Now, it's really easy to go back and forth because once you have this matrix, if you just take the transpose of the matrix, it transforms in the opposite direction. So we're going to see that that's a property of rotation matrices. Okay, so let's do the flip side here. Okay, I'm gonna cheat. I'm gonna copy this from up here. Boom. Got it. And then I'm gonna copy this. So if we start with the vector with respect to the B frame, and we have this rotation matrix that goes from F to B, well, that's no problem. You don't have to like rederive the matrix or anything. You just have to know that if I take the transpose, then this becomes the transformation from B to F. Okay. Guys, I think this lecture's not going to go the full amount of time today. I am blasting through this much faster than I expected for some reason. We'll see. But it's Labor Day, you know. All right, let's talk about some properties of rotation matrices. Some that I just mentioned right here concerning the transpose. So if you have a rotation matrix, and these properties that I'm going to give you, there's two of them. This is a way for you to debug a rotation matrix that you might come up with. You have to check that these properties are satisfied to know that it is in fact a rotation matrix. Okay, so the transpose of an orthogonal matrix. So a rotation matrix is an orthogonal matrix, and this is what it means to be orthogonal as a matrix, that your transpose is equal to your inverse. So the transpose of a rotation matrix is equal to its inverse. And as far as transformations between coordinate systems go, when you take the inverse of the rotation matrix from F to B, it becomes the rotation matrix from B to F. All right, the next property, rotation matrices preserve the length of a vector, which makes sense. They're called a rotation matrix. They just rotate a vector that they operate on. They do not scale the vector. They do not scale it. So what does this mean mathematically? This means that the determinant of the rotation matrix must be equal to 1. So that's something really easy to check in MATLAB. Like if we ask you to derive a rotation matrix check your answer. Take the determinant of that matrix. Oh, wait. I need to change this statement here. It could be equal to plus or minus 1. Wait. I want to write this way. Or minus 1. Minus 1 is like a reflection operation. Okay, guys, to bring this full circle, we're going to do an example of a coordinate transformation. And then we're going to be done for today. And then you can just enjoy the rest of your Labor Day. If you need help with the homework, you can join our office hours at 4:30. You can go for a nice walk outside. You can go for a nice kayak. You go paddleboarding. Good grief. Okay, so here's our example. I want you to express the position vector of this aircraft. Are there office hours tomorrow too, or no? I need to check the syllabus. I know I cover office hours Monday and Thursday. And the TA covers 2 other days. But I'm not sure if he has office hours on Tuesday. Okay, so we have a fixed frame here with origin O. And then we have an aircraft with its body frame. So I don't think there is any on Tuesday. Okay. Office hours Wednesday and Friday. Okay, so we don't have office hours on Tuesday. So the origin of the body frame is at the CG. The X coordinate goes out. The nose of the aircraft. The Z coordinate straight down. And BY is coming out of the page out towards the right wing of the aircraft. And right now, the nose is pitched up 25 degrees relative to horizontal as described by this fx basis vector. Okay. And the distance between point O and point G is 200 kilometers. And the angle in here, 36.87 degrees. So we want to get, once again, the goal of the problem is get the position vector in terms of body coordinates. So first we're going to get the coordinates with respect to the F frame because it's just easier that way. The problem is, the way this problem is set up, that'll be easier to get. Okay, so I'm just writing out what these frames are. BX, BY, BZ. Oops, sorry. Okay, so from the geometry of the figure, the position of the aircraft CG, point G, relative to the origin of the fixed frame, point O, expressed in F coordinates is, so we can see there's an X component. So if you project the position vector down onto this would be the length along Fx. And that length is going to be 200 kilometers times the cosine of 36.87 degrees. So that is 200 cosine 36.87 degrees. And the Fz component, well, this distance is going to be 200 sine 36.87 degrees. However, it's important to recognize that Fz points straight down, whereas this component is facing up. So that's going to be negative relative to FZ. So let's fill this in. 200 cosine 36.87 degrees along the FX direction. Plus 200 sine 36.87 degrees. Oh, sorry, that's minus along the FZ direction. And if you multiply that out, it comes out to something really clean. It's 160 fx and minus 120 fz. So that's basis vector notation. Or if we put it in array notation, the x comes first, the component along y is 0, and then the component along z is minus 120. Okay, so we have the vector in the F frame. So as we mentioned before, our strategy for bringing it to the B frame is to derive a rotation matrix between the F frame and the B frame. Okay, so we're going to get the transformation matrix, and we're going to go through this in gory detail. Just to practice it, drive it home. Would the problem specify if the y component is not 0, since we can't see that in 2D? Yeah, that's right. That's right. Okay. So I'm projecting by onto the different components of F. And this is going to give me a relationship between these different basis vectors. Now, because by is coming out of the page, and because fx and fz are in the page, we know that there's 90 degrees between by and fx, and also between by and fz. And then by and fy, they're both pointing in the exact same direction, straight out of the page. So that's cosine 0. So we started with this one because it's the easiest. Cosine of 90 degrees is 0. Cosine of 0 degrees is 1. And then cosine of 90 degrees is once again 0. So that's by expressed in fx, fy, fz. Let's just blast through this. We're going to project bx onto the basis vectors of F. One reason I like this way of constructing a rotation matrix is because it's, oops, that should be fy. It's very procedural. Like, it makes sense intuitively, like I'm projecting to get the component along each. Once we get into Euler angles on Wednesday, we're going to see it's a little more efficient. It doesn't use as many parameters, but hey, this is tried and true. Okay, so bx and fx, let's talk about that. We know that this component is going to be the cosine of the angle between them. So let's go back up to the figure and see what that is. Bx and fx, we want to see the angle between them. So fx, this vector pointing this way, bx is over here pointing up. So actually, we could see fx is kind of aligned like this. So the angle between them, that's easy. It's theta. It's 25 degrees. So the angle between BX and FX, let's just throw theta in here for now. Even though we know it's 20 degrees, we're going to substitute that later. BX and FY, well, we know that X and Z are in the page, or I mean, they're within the plane of the page. FY is pointing out. They're 90 degrees away from each other, so cosine 90, that's going to go to 0. Now, what about the angle between BX and FZ? Let's go back to the figure. Okay, BX is going out the nose of the airplane. FZ is going straight down. So I could draw FZ like this. So the angle between BX and FZ is this angle right here. And so you can see that's theta plus 90 degrees. Theta plus 90 degrees. All right, so I'm just going to bring these down. Cosine theta, this is going to be 0. Cosine theta plus 90, this is the same as minus sine of theta. So we're just transforming between that. Can you explain why you add the 90 degrees? Sure thing. Sure thing. So look here, we got the dot product between BX and FZ. Because these are unit vectors, this dot product is going to boil down to the cosine of the angle between them. So I'm looking for the angle between BX and FZ. BX is going up through the nose. FZ, remember, it's just pointing straight down. So this wide angle between them, it's theta plus 90. Like you can see that this angle is more than 90 degrees. I hope that's making sense. It's kind of like this. BX, FC, this is theta, this is 90, so I just got to add those two together. Oh, okay, my bad. I thought it was the angle between BZ and FC. Okay, cool. Well, that's coming. That's coming. All right, we're almost done, guys. So now let's look at BZ. We're projecting onto the basis vectors. Anytime we have BZ related to FY, that's going to be a 90 degree. I'm just going to put 0 already. Okay, let's look between BZ and FX. Okay, BZ, it's going down this way. BZ and FX. So that's going to be 90 minus theta. Well, where am I going? And then the angle between BZ and FZ. Yep, that's just theta. Okay. Okay, so 90 degree, cosine of 90 degrees minus theta, that just evaluates to sine of theta, and then we'll bring down this cosine theta. All right, so we have three basis vectors related to each other. Let's fill this in a matrix form. So this is going to be cosine theta 0 minus sine theta. BY was, that one was the easy one, 0, 1, 0. So this is once again called vectrix notation. It's like a matrix of vectors. And this is the rotation matrix from F to B. So that's like one way to remember it. Gasp! It's a direction cosine matrix. Yeah, this is like a standard form that you've seen. We call this a simple rotation. It's a rotation in a plane. And that's when you get situations like this where you have 0, 1, 0, 0, 1, 0. And when we derive a rotation matrix from Euler rotations, it's going to be a succession of these simple rotations in the plane. And that's kind of why I had this example. Uncle Bill. Yellow, y'all. Welcome, Uncle Bill. All right, so if you substitute in our theta equals 25 degrees. Wait, was it 25 degrees? Hold on a second here. Oh, okay, it is. Okay, I thought it was 20 for a second. My B. Okay, let's get some numbers in here. 90630 minus 0.4226. 0, 1, 0, 0.4226. Last week was 340 review. This week is 345 review. Hey man, we are getting back in gear after summer. Everybody needs a review. Okay, this is our rotation matrix. And now that we have it, we're ready to transform, my friends. So we're going to use this. We're going from F to B. The vector G relative to O. So we're going to multiply these out. So to remember once again, the position vector in the F coordinates was 160, 0, minus 120. If you multiply that out, 195.72, 0, minus 41.14. Notice the subscript down here, that's with respect to the body frame coordinates. So this is once again array notation. And we have finished the example. We just blasted through today. Main takeaways. Finding the relationship of a vector with respect to another coordinate frame, it's an issue of projection, and the way we mathematically project things is with a dot product. And so if you do all of these projections onto the three basis vectors of a given frame, you're going to have enough equations to assemble a rotation matrix. And you can see why it's called a direction cosine matrix, because it has to deal with the cosines of the angles between each of the basis vectors. Now, this parameterization, it takes 9 different parameters. Is aeration a valid alternate pronunciation? I haven't heard that. Alternate pronunciation for rotation? I don't know. So this takes 9 different parameters to specify the matrix. When you use Euler angles, it only takes 3. Did I say something weird? Did I mean iteration, or did Srechtenwald mean iteration? Array notation. Okay. Array notation. Arration. Is that what I said? I don't know. Is that what I wrote? Okay. All right, everybody. Wednesday, we're going to go... Aeration isn't a word y'all had me thinking it was. We're going to go into Euler angles and finish that up. The next homework is going to be up today. Actually, I think it might have automatically posted, but I need to change the due date. Okay, no, I'm gonna post the next assignment today. It'll be due Wednesday of next week, and this homework has to do with rotation matrices, so it's fitting. So once again, office hours 4:30. I'm gonna hang out here for another couple minutes. If you guys have any questions you want to throw out here, other than that, I think I'm gonna get a couple things ready in the meantime, prep some homework, post that. Turn up the tunes a little bit. Oops. I was having trouble with the transfer function on the homework. What was giving you trouble? Could you reword the second half of problem? The second half of problem 2, part D. Oh, what is that? Let me look at it. Problem 2, part D. Let me pull it up. This problem 2, part D? Wait, what's wrong with this one? Okay, so find the transfer function from the elevator input to the angle of attack. So transfer function, it's why are you guys saying D&E or whack, man? Okay, a transfer function is the Laplace transform of the output relative to the Laplace transform of the input. So the input is the elevator angle, and the output is the angle of attack, right? So you're going to get that transfer function from this. So this is the linear perturbation equation, right? So if you want to get the transfer function, the first step is to take the Laplace transform of this. Don't let all these deltas fool you either. Like, I submitted my homework like 30 minutes before you sent the email. Am I allowed to resubmit? Oh, yeah, you can resubmit. I allowed unlimited resubmissions, so we'll just grade your most recent one before the deadline. You know what I mean? So like this whole term right here in front of the delta alpha, that's just a constant. Like you're just gonna plug in the equilibrium angle of attack here. So all of this out in front is just going to evaluate to a number. And then B and C, those are just numbers. So you take the Laplace transform of this, and then you just form the ratio of the elevator angle as a function of S divided by the angle of attack as a function of S. For 2C, how many lines are we supposed to have plotted on our graph? 2 or 3? Simulate initial conditions. There should be 2, because when you simulate like the linear perturbation model, it's going to give you 2 lines. It'll give you delta alpha as a function of time, and it'll also give you delta alpha dot as a function of time. But we're just asking you to compare alpha to, so you don't have to worry about the dot. So the Laplace transform of the perturbation model is the output for the transfer function. Hold on, so for part D, can we just pick the frequency corresponding to the highest amplitude from the Bode plot? Well, what does that mean? I'm going to guide you. And what is it asking for? For an input elevator angle that's sinusoidal, what frequency will produce the largest state amplitude? Do you know what the Bode plot physically means? Do you know what the Bode plot physically means? No! Okay, let me tell you what a Bode plot physically means. So, no, I have a small brain. It has nothing to do with that. So a Bode plot, it has frequency, or omega, typically in radians per second on the horizontal axis. The vertical axis is, just in simple terms, it's the amplitude ratio. What does that mean? The amplitude ratio is output amplitude divided by input amplitude. Now when we plot it in decibels, I don't know, you might end up with something like this for a second order system. And at a given frequency, let's call this like omega naught, this is the input frequency, by the way. So it means if I take my system and I provide a sinusoidal input at this frequency, feedback, this deserves a few minutes lecture time in future years. Okay. Yeah, I guess we're reviewing a lot of stuff, so we could review this as well. So at this frequency, I come over here and I can see this is the amplitude ratio at that frequency. So all this means, let's say that I come over here and at this frequency, the amplitude ratio, what if it's like 5 or something? Earlier you said that for the transfer function we'd have to solve for delta over alpha. But since we want output over input, shouldn't we solve for alpha? Okay, you're exactly right, Kyle. I misspoke if I said that it was delta over alpha. I misspoke. It's definitely alpha over delta. So let's say the amplitude ratio is 5. That means that if I give an input of, let's say it's like u of t is 2 sine omega naught t. So it's a sinusoid at that frequency with an amplitude of 2. This means that the output is going to have 5 times whatever the input was. And like there's going to be some phase shift, but this homework you're not really worrying about that. But that's what the amplitude ratio means. It's how much the amplitude of your output gets scaled. So, wait, who asked about this? Rue, do you know what to pick now? Scroll back. What's the y-axis again? It's the amplitude ratio. Oh shoot. Amplitude ratio. The ratio of output amplitude to input amplitude. Our output amplitude comes from the Laplace of the perturbation. Yeah, well it turns out, so I'm just trying to give you a physical interpretation of the Bode plot first, so you understand what it means. But where this amplitude ratio comes from mathematically, it is related to the Laplace transform because it's equal to your transfer function. Let's call it g of s. It's a function of s when you take the Laplace transform of your transfer function. You evaluate that transfer function at s equals I omega, and then you take the magnitude of that. And that is what the amplitude ratio is. So it turns out, if you have a transfer function, transfer functions are in terms of s, right? If you substitute in I times omega for s, and then take the magnitude of that, that gives you the amplitude ratio as a function of omega. So I mean, that's what MATLAB is doing when it runs the Bode command, right? You give it a transfer function, and then it evaluates it at I omega, takes the magnitude, and it returns the Bode plot. Specifically, it plots it in decibels, though. So when it plots it, it does 20 log base 10 of your amplitude ratio. That's what decibels means. Output through the transfer function, right? Yeah, it's the output of the transfer function. For omega, we can just choose any lens space row vector and send it through. You could, but the MATLAB does it for you automatically. If you just use the Bode command of a transfer function, it will pick a range of omegas, which will capture the dynamics. But you could also provide your own lens space of omega if you wanted. And then these values all graph on the time axis and would have a unique value at 120 Hz. I'm not sure what you mean. I'm not sure what you mean by that. Tilde rows. These values all graph. Does amplitude ratio also change with respect to time? Oh, maybe I see what you're saying. Well, this Bode plot, these amplitude ratios of input to output, this is at steady state. Now what that means is steady state. Do you know what steady state means? Like if I have, which of these with respect to time and which aren't? Which of these with respect to time and aren't would be my question. Okay. Well, I mean, a Bode plot isn't with respect to time. Like if I provide an input, oh, that doesn't look good. But let's just say it's a sinusoid, and it has, you know, that's the amplitude of the sinusoid. If I give this, let's say I provide that as the input to a transfer function, g of s. So what's going to come out is my output, y of t over time. Now, when I first start applying this input, I might have some like transient response. Oh, that looks terrible. Alright, we'll do like something like this. And so maybe the amplitude is changing, but after a certain amount of time, so once we reach steady state, the amplitude will reach a steady state value and it won't change anymore. It'll stay like within these bounds. So the amplitude ratio, like the ratio of input to output, it looks at this steady state region. Let's call this like A2, the amplitude of the output at steady state. And the amplitude ratio is comparing these values, you know, like A2 over A. So at steady state, these amplitudes don't change anymore. So when you look at a Bode plot and you look at the amplitude ratio at a given frequency, oh, where did it go? It's saying like, I'm talking about a steady state amplitude ratio. So then what if A is not a constant and the function has different amplitude zones as a higher order? Will it then resolve to steady state? Well, that's what I'm saying. A is there's different amplitude zones. Even if your input has multiple frequency components, you can break it down. Because that's part of the point of a Bode plot. You might have a complicated input that is a superposition of many different sinusoids. So you can still break that down into its individual pieces and say, this component of my input is contributing this amplitude ratio at steady state. Yeah. So the amplitude ratio is about resolved, steady motion. Everything's at steady state. It does not apply to transient dynamics. All right, everybody. I'm going to take a little break. I'm going to be on Discord from 4:30 to 5:30. If you have more questions. Okay, so it could become a puzzle of many pieces, just like the transfer function is layered. It has layers, you know, like onions, like ogres. They have layers. And with that, see you on Discord. With that, I'll leave you.